so we are quite happy to have Mohammed and Kunbo Kim. So they both will be speaking on something in SPDE. And I think many of you would have heard Mohammed is probably his third visit. Hopefully the third one also could have been in person, would have been nicer. And so he'll be speaking on some non-existent results for the stochastic wave equation. Yes, Mohammed.
Well, thank you, Yogesh. So I'm very happy to speak at the Bangalore seminar again. While I would have liked to be there in person, but unfortunately due to the circumstances, it's impossible these days. So I'm going to talk a bit about some non-existence results for the stochastic wave equation. So I remember last time I talked about the stochastic heat equation, but I'm going to give you a bit of the right background in order for you to understand what I'm going to talk about. So let me just begin by saying that while working on the problem, I realized that there are not a lot of papers on non-existence for the stochastic equations as opposed to the deterministic equation. So I think that's a really good topic of investigation, and I think there is quite a lot of there are quite a lot of things to do in that area. So let me just begin by giving you the plan. So I'm going to talk a bit about the stochastic, the heat equation first, and then I'm going to move to the wave equation. So here are the main references. So the first paper is essentially the starting point of this whole project. And so that was for the heat equation. And for the wave equation, a good paper is an old paper by Robert Glassy, where he studies blow-up problems for nonlinear wave equations. So this is a deterministic paper. And my talk is going to be based on joint work with Eulalia Nualart. So the first paper is on the heat equation, and it's, I believe, has already appeared in Bernoulli. And the second one, which deals with the stochastic wave equation in one dimension, is going to is still under revision. So let me just talk about the heat equation problem first. So we're going to look at an ODE. So if we consider this little ODE here, I have dy by dt equals to b of y. So here b is always going to be assumed to be only locally Lipschitz. And we are going to assume also that it is positive, increasing, and sometimes convex as well. So those conditions do not matter that much. Well, it does matter, but the most important thing for us is the integrability condition that I've just put here. So T here. So we want to understand when this ODE actually blows up. So this is a very simple example problem, which essentially you can give your student to solve. So essentially you just take the b on the left-hand side, the t on the right-hand side, and then you integrate, and then you get this fact here, that it is going to blow up in finite time if and only if this is this integrability, this integral on the right-hand side is finite. Okay, so now let's actually perturbate my ODE by a noise term. Okay, so I have a simple ODE with additive noise in this case. So it turns out that this solution is going to blow up. The solution is going to blow up almost surely if and only if 1 over b of SDS is finite. And there are a couple of ways of looking at, of finding this. One way is to just apply Feller's test for explosion. So what you do, you just test. You have the well-known Feller test for explosion. You just apply it and you get the condition, right? So another way of doing it is essentially to look at it from a deterministic point of view. You say that while the Brownian motion is going to grow as time goes to infinity, the supremum of the Brownian motion is going to grow. And then you use this fact to show that this integral equation blows up in finite time. But the intuition here is actually clear. So Brownian motion tends to push the solution up so that the deterministic part starts kicking in. Right. So that's a bit of a simple example, but it's quite important because it tells us how to attack the problem for more complicated equations, especially for SPDE. So I repeat, this is not actually, I mean, the intuition also is a bit misleading because Brownian motion does not, well, it oscillates, so it can also go down. But when it starts going up, it goes up for a long enough time so that if this condition, if my integral condition is satisfied, it's enough to actually induce blow up. Okay, so it's not enough. I mean, the last line is actually not quite precise. And I have to say that I won't give too much precision in this talk, but I really want is to give you a flavor of what's happening. So you could look at from the deterministic, from the ODE, you could look at the PDE. So essentially here we have a Laplacian, which is here to my ODE, so that becomes a PDE. And here I'm going to focus on the Dirichlet boundary condition. So it might look like a problem which is just a purely mathematical problem, but these kind of models are very useful because it can actually model quite a lot of things. For instance, you're heating a container with zero temperature at the boundary, and you have a heat source which is given, an external heat source given by BU. So you would want to know whether the object or the material that you're heating up cracks or not. So the blow up problems are very important in practice because it actually means that you can have cracks, and the temperature goes so high that you have cracks in the system. So it's quite important to actually study those. And it comes up in the variety of settings. So my point is that it's just not a purely theoretical question that mathematicians would like to study, but it has some practical implication. So what's happening in this case? Well, you have the same condition, but it turns out that it's not going to blow up if your initial condition, U0, is small. Well, I'm not going to go into much detail of how small this U0 has to be, but I just wanted to convey, to tell you that it's not going to blow up even if we have this integrability condition. So for an ODE, it does blow up, but once you have the Laplacian here, it doesn't. So it turns out that the Laplacian has the effect of pushing the solutions down. The Dirichlet Laplacian, by the way, pushes the solutions down very quickly, so that if your initial condition is small, it's not enough for the solution to blow up. And that's the intuitive idea here. So now let's perturbate this equation with space-time white noise. Now, what's going to happen? Again, saying that the white noise is going to push the solution up is not enough. It requires some kind of a proof, but this is effectively what's happening, right? So I have my space-time white noise, so meaning that intuitively you could think of it as I'm putting the noise in an independent way in space and time. So what happens is that this intergravity condition now is enough for the solution to blow up in finite time. So that's quite interesting because it tells you that no matter what the initial condition is, and in fact, no matter what, how small the noise is, if I can just put an epsilon in front of the noise here, it's still gonna blow up in finite time. Okay. So I cannot, we can have estimates on the blow up time, but I'm not gonna go into too much detail here. So essentially, that was the starting point of our current research. So we wanted to know what happens if you have the stochastic wave equation. So what kind of condition do we have if instead of the heat equation, we have the wave equation? So it turns out that this is very, the problem is not as straightforward as for the heat equation. So the wave equation has a lot of challenges, and I'm going to talk a bit about that later. But for the time being, I want to actually go tell you what is the proof ideas. So for the heat equation here, so what you need to be doing, and that's essentially the main ideas behind a lot of the papers that you see, a lot of those kind of results. So the idea is essentially try to compare your solution with or an object relating to your solution to an ODE. Now, for the deterministic case, you compare it with a nonlinear ODE. For stochastic case, you compare it with an SDE, which blows up according to Feller's test. Okay, so essentially that's the current. This is the current route that most of the papers looking at these problems. So here, what we do, the object that we look at, we essentially hit it with phi of x, which is the first eigenfunction. So we're looking at it on 0, 1. So we look at the first Dirac eigenfunction. So we smooth our solution with respect to that eigenfunction here. So we get an object which is y of t. And then for the deterministic case, we get an ODE of the following type, or an integral equation of the following type. And then you can actually show that it blows up in finite time. Now, for the stochastic heat equation, you get an SDE of the following type. Okay, not quite exactly the same, but of the same type. And then you can actually use Feller's test for explosion. So one of the things that needs to be said here is that for the heat equation and for the stochastic heat equation, we are using comparison arguments quite heavily, right? So because you're not going to get, like I said, you're not going to get the ODE and the SDE exactly, but you're going to bound your solution above and below by SDEs of the following type. So comparison principles are quite important in this business, right? And this is what I write here: comparison principle. And once you know that your YT is blowing up, then you have that the supremum of the solution blows up as well. And this is what we mean by blow up or non-existence of global solution. So one thing that I have to say here is that yeah, so comparison principle is quite important. And for the wave equation, we do not have such comparison principles. So that's going to be one of the challenges. You can do it in a higher dimension for the heat equation, but you will have to change the white noise to a colored noise. So that can actually be done as well. There are quite a lot of things that you can actually do, and which I'm working on right now. So for instance, you can have a multiplicative noise and try to see what happens. It's also not clear. I've seen one paper looking at multiplicative noise, only one paper that I've seen. So if you guys know more references, please let me know. Yeah, so this is something of a problem which hasn't been discussed by quite well, a lot, I think. So Carl Mueller has a few papers as well, but what he studies is essentially a blow up due to the noise term rather than the additive term. So here, in this talk, or in my research that I'm trying to do, is that I'm trying to look at additive blow up due to the additive term and the multiplicative term as well. While there are some papers who just look at blow up due to the multiplicative noise. So they just put U to raise some power and try to understand non-existence of blow up. So yeah, so for another difference from the wave case is that here, for the stochastic case, we are looking at almost sure blow up. Because Feller's test in this case, under this condition, will give you almost sure blow up. And for additive noise, this is exactly what happens, right? For multiplicative noise, that's most likely not going to happen. You might not get blow up almost surely. You will get blow up with a positive probability. But I'm digressing a bit here now. So let's go back to the wave equation. So before looking at the wave equation, let us look at the second order ODE. So the reason that I'm putting the ODE first is because we want to think about the problem the same way as we did for the heat equation. So at the end of the day, what we will want to be doing is to compare my stochastic wave equation with some kind of integral equation. Even though I've told you this is not easy. So that's the reason why I'm looking at the stochastic, at this second order ODE here. So if I look at this second order ODE, I want to know when it actually blows up. So this is a calculus exercise again. I'm rewriting it as an integral equation by just taking the integral on the right hand side twice and using I change the order of integral and I get this t minus s here. So the solution will blow up if only if I have this integral condition here. So as you can see, this is very different from the previous condition. And it's kind of nice to actually look at how you come up with it. So the way you come up with it is quite simple, to be honest. So you write your ODE, you just multiply by y prime. So your ODE is a second order ODE. You just multiply this by y prime here. And then you realize that when you differentiate y prime squared, you get something of that type. So that you can take integral on both sides. And then this term here becomes this here. So then you have y prime equals f of yt, and then you can use the conditions for the first order ODE. This is not quite surprising. Usually when you want to look at second order ODE, then this is what we teach our student. You reduce the order, and that's what we did here. But it's kind of nice to look at how the conditions come around, and that's exactly what happens. So, and that's the reason why you have the square root on here. This is because of the y squared here. So it's a bit of a calculus trick, which I always find nice. So yeah, so that tells you what is the condition that you need to be looking for. So if you believe in the intuition that when you have noise, the noise pushes the solution up, and then the mechanism for blow up becomes a deterministic mechanism. So then you would guess that this is the right condition for blow up. Okay. And that's the reason why we looked at it, because we kind of guessed that, this essentially should be the reason, should be the condition, if we believe in the intuition that the noise will push the solution up, and then the deterministic mechanism will kick in. So we wanted to actually prove that. So it turns out that this is not going to be as simple as the picture, at least, is not going to be as simple as the heat equation, which is to be expected, because the wave equation is never as clean as the heat equation. So let's look at the deterministic wave equation here and see what is the condition. So obviously people have already looked at this problem in the deterministic setting. And as I said, for many reasons. So the condition is essentially very similar to that of the second order ODE, except that here you see how the Laplacian comes in directly in the integral condition. So again, phi here is the first eigenfunction of the Dirichlet Laplacian. Mu is the first eigenvalue. Okay. So I have some, we need to impose some further conditions on B, but I'm not gonna give you those conditions here because they're a bit technical, and because we are just interested in that integral condition. But the paper by Robert Glacy has all the technical details, and that's the condition that you have. And again, the idea is the same. What you want to be doing is you want to multiply your solution, well, both sides of your equation by phi of x, and then come up with an ODE, a second order nonlinear ODE, and then you just apply this fact here, and then you get this condition. So if you're a bit experienced with that kind of computation, you can see exactly what happens. See that the b here, when you multiply by phi of x, you pick up a minus mu of s, just because the Laplacian is pushing the solution down. And then when you integrate that, you get s squared here. And that's the reason why you have the mu s squared here. So again, the intuition here is that if I add my noise, I perturbate my stochastic, my wave equation by a white noise here with the same condition, then it doesn't really matter. The Laplacian, the effect of the Laplacian will go away, just like for the heat equation. Okay, because the solution is going to be pushed far high enough so that the Laplacian does not have much of an effect. Here I have to really mention that something important about initial condition here. So we are always assuming that our initial condition is non-negative and as nice as we want. So we don't want to really care about the initial condition. Really, what we really want to care about is the integrability condition. Yeah, so that's the intuition. So one thing that happens is, unlike, like I mentioned, unlike for the heat equation, we don't have almost sure blow up. We have blow up only with positive probability. We don't know whether our result is the best, or that we can actually get in that sense, or whether we can actually make the positive probability becomes almost sure. We don't really know that. But I'd like to actually talk about the proof now, because the proof is essentially, it will follow along the same line, but it's a bit different. And you're going to see exactly how I get the positive probability, and maybe someone in the audience can tell me how to improve it. Okay, so let me now look at this equation, the wave equation, and give you an idea of the proof. So, as usual, for stochastic equation, we don't look at the equation itself, because we don't have a differential calculus, we have an integral calculus. So we're going to look at the solution, at the integral formulation of the solution. So here, as opposed to the deterministic case, the third term, the stochastic term, is essentially the most, the trickiest one. That's the cause of concern, right? But this is actually well known. You can actually make sense of it in the Walsh setting. So we'll assume I'm not going to talk too much about how to make sense of that. But I'm going to tell you another difficulty that arises in the wave equation as compared to the heat equation. Here we cannot use comparison principle because we don't have such a comparison principle, or such nice comparison principle. So the difficulty is that your wave the kernel G is not very well behaved. And what does that mean, not very well behaved? Well, I'm going to tell you in the next slide. But it turns out that for small times, you can actually compare an object, well, use some kind of comparison principle. And that's one of the observations that we made, that we can actually do it for small times. Or like for a certain time, I should say. You can argue that the times are not that small, but yeah. So like I said, difficulty is that the kernel is not that nice. So in that, what I mean is that, you know, this here, the sign here is actually oscillating. So you cannot really compare it with a nice function. So, but I'm still going to do that, because when I multiply by phi1 here, which is the first eigenfunction, so everything goes away. You're left with sine, and everything now. So you're left with sine pi over t. And if you go back here, so let's forget about the first two terms here. If you look at the last term here, I'm going to have sine t minus s. But obviously sine, I can actually bound it below by t minus s for a specific time interval. And that's one of the main ideas behind it. Like I said, the idea is to compare yt with an integral equation in a certain time interval only. So how do I do that? So for the deterministic part, meaning that for these two parts here, this is not much of a problem. The problem here is for the term which contains a non-linearity. And I can do it because I'm left only with sine t minus s, which I can bound below by some nice constant t minus s for a certain time interval only. And the other term, which I'm going to talk about, is this one, this term here. Now, this term, I will need to make it as big as possible. And you're going to see why. So this term is actually a Gaussian process. So I'm going to multiply it by phi of x dx, and I can rewrite it as the following, right? Because modular constant, I would say. So my infinite sum here, everything goes away, and the only term which survives is phi1 of y. This is because they are all perpendicular to each other. So I'm left with sine t minus s dbs for some bs, because when I integrate 0, 1, and I integrate this guy here, the white nose here, I get some Brownian motion. Now, the good thing about it is that this sine t minus s is obviously deterministic. So this is not an stochastic integral. This is no longer a stochastic integral. So I can actually write it as cos t minus s bs here. Now, like I said, I want the integral, the stochastic part, to be as big as possible. And that's essentially the intuition behind my strategy, is that the stochastic part will just push the solution up. So how do I do that here? So while in this case, there are different ways of doing it. One way of looking at it is that you have a support theorem for Brownian motion, which tells you that you can actually make your Brownian motion go as high, high enough in a certain time interval. Here, I have to make sure that the cosine doesn't go to 0, right? So I need to actually do the whole computation in a time interval, so that the cosine here is just bounded below, so that here my Brownian motion can be pushed with a positive probability. And that's where the positive probability comes in instead of the almost sure probability that you get for the heat equation. So in these slides here, you can see exactly what are the issues as compared with the heat equation. Because at the end of the day, we'll be looking for the heat equation also, we'll be looking at an integral formulation of the solution. The wave equation is a totally different beast. This is mainly because of in our case, mainly because of the green, because of the kernel here, which behaves very differently. Okay, so you have some nice heat kernel estimates for the heat equation, but here, those estimates are just not that nice. And in fact, everyone who knows about the heat equation knows that as you go in higher dimension, you get more into trouble. So here we're just sticking with one dimension. We are also assuming it's actually, this is more important than for the heat equation, that the initial data is actually non-negative. Things are not that easy if you relax those kind of conditions for the wave equation. And I'm not even talking about the stochastic wave equation, I'm just talking about the regular wave equation without the stochastic. So the wave equation is a really different kind of equation as the heat equation. So yeah, so back to my strategy. So MT is actually large now. I can actually prove that MT is large. And I can compare YT. Recall that my YT was given by this fact here. And I can compare it now with something of that type, where I have an L here, which I can make as big as I want with a certain probability. Right. So for blow up, we just need this integral condition to be satisfied, because I'm just going to compare it with what I had earlier. So this is the same kind of condition. But now here, I need to make sure that my blow up occurs within that time interval here. And I can do that by just taking L as large enough, because this essentially will give me the time from T0 for it to blow up. So that integral here, since it is finite, and since I have my nice conditions on B, I can make L to be large enough so that this is my solution is going to blow up within that time interval. So essentially, that's the main idea behind it, and that's the reason why you kind of find such integral condition, which is related to this integral equation here, which is in turn related to the second order ODE. So the main take-home message here is that the wave equation also have some kind of similar phenomenon. The stochastic wave equation also is essentially dominated by the noise term, which pushes the solution up. But in this case, we are only able to prove much less because we can actually do it only with a positive probability. And again, I don't know whether it's the strategy behind the proof, or it's just something to do with the wave equation. I think that you will not get almost sure blow up for the wave equation under this condition. So even though our methods are not that sharp, the result in some sense is in that sense. So, but we can actually do much better if we look at the wave equation on the whole line, and for that you need the following observation here. So if I have this integral condition, this integral equation, which is related to the second order ODE, and I perturbate it with a GT here, which grows to infinity in some sense. So this could be oscillating. So think of a Gaussian process here, which in some sense the supremum goes to infinity as t goes to infinity. So it turns out that the same integral equation will guarantee blow up. And again, this is just a matter of comparing it using comparison principles. So this is a deterministic fact. B here is always going to be positive and increasing. So there's no issues comparing doing those comparison principles. But this is quite important because you can look at the equation in the whole line now. Again, I'm looking at the white noise here, and you see now the difference between the whole line and the domain with Dirichlet boundary condition is that the solution now blows up almost surely. And the way that we do that is essentially the same as that of the heat equation. So you write down your integral formulation of the solution. Now it's a bit different in the sense that the green function now is slightly better behaved. And the integral here is on the whole line. So the deterministic equation here, the stochastic part is actually a Gaussian process. So it's completely determined by its correlation, which you can actually compute. And using that, you can have the following fact here, that it satisfies some kind of law of iterated logarithm. And recall that I have a t here. This is different from, say, Brownian motion. And this requires, this follows from standard Gaussian theory, which you can actually use to prove it. And once you know that this is actually growing as big as we want, and this is almost sure, you can compare it with the following integral equation and get blow up under this condition here. And I should mention that here, this equation here, you see alpha and beta, which is different from A and B, and this alpha and beta can be any positive number. And essentially that's how you get the result. So the main point is that I wanted to make by giving you the last theorem is that if you change the initial the boundary condition, you put it on a whole line with the space-time white noise, instead of getting blow up with positive probability, you get it with almost sure. And this essentially follows from the fact that the stochastic term grows very, very high, almost sure. And I think I'm going to stop here.
Thanks, Mohammed. So if there are any questions, please feel free to ask. People can unmute themselves and ask, or post it on the chat, and I can ask Mohammed.
I have one question.
Yeah, sure.
Mohammed, you may have mentioned this or even thought about this, but there's a way to transform the wave equation to the Brownian sheet, right? Are there Wiener tests available for the Brownian sheet in some sense? They'll explore.
Which test you're saying?
No, your explosion test, your Fuller's explosion test, for example.
Yes.
For the Brownian sheet, are they available? Then you could use those for the wave equation.
Ah, okay, okay. So you're saying that, you know, instead of going through the process that I did, I could just rewrite it as a Brownian sheet, you're saying?
Yeah, that's right. That's right. Yeah, the two parameter.
A 2-parameter Brownian sheet, and then use that to get the blow up.
There may be tests there. I don't know.
Okay. Okay. No, that's an interesting fact, actually. Yeah, thanks for that.
Can I ask a question? I'm Abhay from ISI Delhi.
Yeah.
Yeah. So it's a very naive question, but in SD, one can talk of diffusions with jumps. So is there
Yes.
any such concept for waves with shocks or something? And if so, does this question make sense? Explosions for such objects?
Well, yes, it does. That's an interesting question. First, let me just tell you a bit about the heat equation. So the heat equation, you could perturbate your white noise by something which jumps, right? And then you can get the same kind of result. Okay, so there's nothing special, provided that you make good sense of the solution, right? And you could do the same thing for the wave equation, except that here, okay, let me just go to the so this term here, instead of having white noise here, you're going to have your jump process, which could be like some kind of a levy noise. And then you will have to actually make sense of it. Okay, so making sense of these kind of equations with some kind of jump noise has been done before, and it does make sense to look at the same kind of question. And I believe that this is going to work because what you will need to actually prove is that this NT here is actually growing up. And I think you will be able to do that, but I haven't tried. And to give you a better answer here, so this G here, even if this were actually discontinuous, it will still work because we are not using any continuity fact here when you compare it with when we are actually getting this intergravity condition. So here you could have some jumps, right? GT, but as long as it grows up, you could that it grows to infinity, you can actually pull off the same kind of arguments.
Thanks.
Mohammed, I have one question. The last part where you said, you get you use that if you take a white noise and then you're convolving it, you get a Gaussian process, and you get the bounds using Gaussian process.
Yeah.
So, but this should work. I mean, what is the? It should work even if you don't have a white noise, maybe a colored noise or something, some other noise, some Gaussian structure is all you need. Is that?
Yes. So you need only the Gaussian structure. So I have to say that this is essentially the baby version, right, of these results, essentially, because I just wanted to convey the idea, right?
Okay.
But you got it. I'm happy you got it. So because you could actually put any sort of noise, which is actually Gaussian, and this theory also here is also a very general theory. All that we did in order to get this is to compute the correlation structure and so that it will grow. So essentially, there's a whole theory which tells you that while you're given a Gaussian process, whose correlation satisfies some condition. Hence, it's gonna grow in a particular way, and that's what we use, and that's what you need, like you said.
Okay.
Yeah.
Okay. So if there are no more questions, I will ask the participants to unmute and give a round of applause for Mohammed.